Hello all. So this presentation is a real life case study with actual data presented to help in deciding whether one needs a waveform every few minutes or every few hours, or how to decide an appropriate sampling rate for predictive maintenance of radio equipments. So all the different operations in basically in for machine operations in the industry can be categorized into four: constant load and speed, varying load and speed, constant load and varying speed, and varying load and constant speed. Out of these, the first two are most realistic and covers most of the applications in the industry. We will talk about constant load and constant speed in this particular presentation, which will form the basis for varying load and varying speed kind of operations too. So we're talking about, we basically use the industry famous data set available from NASA's Prognostic Center. In this experiment, a 1200 RPM machine was run continuously for 7 days. It had 4 bearings, bearing 1, 2, 3, and 4. And at the end of day 7, the outer race failure happened on bearing 1, where, as you can see, 2 accelerometers have been mounted. And we took the data set from those accelerometers. You can actually download it from this link. The accelerometer was 20 kilohertz rated, and was measuring a sample with 20,000 cycles per second in 3 directions every 10 minutes. So we calculated the RMS of each sample for every 10-minute data or 30-minute data, 1-hour data, 6-hour data, and 12-hour data. What we noticed that it was consistent in every case that relative to the baseline, and what we call a baseline is something like this. So relative to the baseline, the first peak in each case was detected at 7,021 minutes or within 3 hours of the same. What this showed is even with a waveform of every 10 minutes or every 3 hours or 6 hours, one would have been easily be able to detect an anomaly in RMS data, regardless of how soon we take in waveform data. Now, when we come to BPFO, bearing pass outer race failure, fault, and when we selected the harmonic with the maximum amplitude for the BPFO, what we noticed is, and when we compared it for every 10 minutes, 30 minutes, 1 hour, 3 hour, 6 hour, and 12-hour data. Again, here we notice that relative to the baseline, and this is the baseline that you can see. So relative to that baseline, the first peak in BPFO amplitude occurred between 2,000 to 9,211 minutes and 9,361 minutes. That is within 6 hours. So that means with every 10 minutes, the waveform data, one will be able to detect an early bearing outer race failure 8% in advance, because the first early advance happened somewhere here. So 9,211 divided by total of 10,000 minutes is what this ran. So it's around 8% in advance. While with every 6-hour or 12-hour data, you will see that 7% in advance, which means even though the waveform upload frequency or FFT frequency has been increased to 36 times when we take waveform every 10 minutes as compared to every 12 hours, the advance warning only increased by 1%. That means if the motor MTBF is 4 months, with every 10-minute time waveform, one would know 10 days in advance, while with every 12-hour data, one would know 9 days in advance, with obviously with almost 100% accuracy. So it is clear that the unplanned downtime could be easily avoided by both every 10-minute waveform data and even every 12-minute waveform data. And we noticed very similar trend even for BPFI. Now, when we try to compare how much it would cost in terms of power, data costs, or cloud computing costs for every 10-minute waveform data as compared to every 12-hour waveform data, with every 3-hour data, as you can see, on 50 million monitoring electric motors in the 50 million monitorable electric motors in the world present, we are looking at an equivalent of 6.4 million cars of CO2 taken off from the Earth when we do every 3 hours as compared to every 10 minutes. And the same goes to 6.5 million cars of CO2 taken off from the road when with every 12 hours as compared to every 10-minute waveform data. So what this really tells is that we usually ignore the power costs because of these sensors as very, very small. But the point is, when you take it on a very consistent basis and multiple sensors per machine every day and over the year and for millions of motors, it quickly adds up. That's just the power cost. And when it comes to the data cost, it's even more higher. So just the data cost of 1,000 sensors per year for every 10-minute waveform would be close to $275,000 as compared to mere $9,000 per year with every 3-hour waveform data, and $2,200 per year with every 12-hour waveform data, which is completely manageable. While the major cost is the cloud computing one. So based on our own internal cloud computing cost, for 3,200 sensors with every 6-hour data, it costs us almost $2,300 per month, whereas it would cost almost $140,400 per month with these 3,200 sensors if we take a waveform every 10 minutes. For a large conglomerate company that we know that has up to 80,000 sensors installed, this can cost almost $42 million per annum with every 10-minute waveform data. While with every 12-hour waveform data, these costs are well manageable and will be as much as just $350,000 per annum. So to conclude, what we see is that it is really unnecessary to take waveform data every few minutes, as it neither increases the fault diagnosis capability nor is efficient from the perspective of power, data cost, or cloud computing cost. Apart from this, even the RMS of the time waveform can be calculated on the edge without the need to send the whole waveform every few minutes, thus having the ability to be able to wake up the sensor for any anomaly very quickly, and taking the big data upload at that time easily compensates for whatever one can do by taking the waveform and sending to data. So really, sending to internet is not required at all. For truly scalable solution, it is mandatory that the data filtering is done at the edge and only certain times a day, let's say 4 times a day, or based on an event only, the time waveform or FFT spectrum should be sent to the cloud appropriately. So that was for constant load and speed case. Now, in case of a varying load and speed case, usually the load is inversely proportional to speed. In the constant speed and constant load data, the baseline is rather narrow, as you have seen earlier. It looks more like a straight line with very minor bumps or changes. Means the standard deviation is really low. As compared to that, in case of varying speed and load, this baseline looks more like a range, as you can see on the screen, with an upper limit and the lower limit representing a range within which most of the values fall. But as the fault starts to progress, this range itself moves up. And thus, for such case, we can easily take the waveform at a larger interval, like let's say every 2 hours for the initial few days to form that range. Once the range is formed, then again the waveform data frequency can be reduced to somewhat like once every 6 hours per day. All this while taking RMS of the waveform every 5 or 10 minutes, so that anomaly can be detected every few minutes, just like we did in the constant load and constant speed machine. This will still ensure that this kind of approach is good, not just for constant load and speed machine, but also for variable speed and load operations, while reducing the power requirements, data costs, and cloud costs drastically.